Hello, my name is Resul Ayberk Şahpaz, and this is the presentation video of our Physics 211 project. In this project, we investigate stress distributions in transparent materials using the photoelastic method, with particular focus on thermally induced stresses in glass and mechanically induced stresses in plastic specimens. Photoelasticity is an optical technique that exploits stress induced by refringence in transparent materials. When such materials are subjected to external forces or temperature gradients, differences in the principal stresses lead to changes in refractive indices along orthogonal directions. As a result, polarized light passing through the specimen experiences a phase shift, which becomes observable as isochromatic fringe patterns when analyzed with a polariscope. The theoretical basis of this method is the stress-optic law, which establishes a linear relationship between the phase retardation of light and the principal stress difference in the material. This relationship allows fringe order to be directly correlated with mechanical or thermal stress, enabling both qualitative and quantitative analysis. Experimentally, two types of stresses were examined by our group. First, thermal stress was induced by local heating a glass specimen using a lighter. Prior to heating, no birefringence was observed, indicating a negligible internal stress state. Following localized heating, distinct fringe patterns emerged, particularly around the heated regions. These patterns become denser near areas with higher temperature gradients, in agreement with thermoelastic theory, which predicts stress generation due to constrain thermal expansion. Second, force-induced stress was investigated using plastic specimens subjected to axial compression and bending. When external forces was applied, clear stress patterns appeared under polarized light, with fringe concentration increasing toward the central regions of the specimens. This behavior is consistent with classical beam theory, where bending stresses are maximal away from the neutral axis. To support the experimental observations, numerical simulations were conducted using Python and ANSYS. The simulated stress and fringe distribution showed strong agreement with the experimental results for both thermal and mechanical loading cases, validating the applicability of the stress-optic law and under the experimental conditions. In conclusion, this study demonstrates that photoelastic stress analysis is an effective and reliable method for visualizing stress fields in transparent materials. The consistency between theoretical predictions, simulations, and experimental observations confirms the validity of the approach. Despite material and experimental limitations, the fundamental physical behavior was successfully captured, highlighting the utility of photoelasticity in experimental stress analysis.